All right. So welcome back, everybody. It's time to start again. Today's lecture is about the Bayes filter and the Kalman filter. We'll be using some of the things that we have explained in other lectures, but just let me remind them very briefly. So in previous lecture 2, what we discussed is on the expectation operator, right? So there we were doing some manipulations, and then we were also, calculating means and covariances, right? We also define a Gaussian distribution. In this case, for us, it's more interesting the multi-dimensional problem. And then there was this particular problem on covariance transformation, right, which we discussed for an affine transformation that is this, and then a nonlinear transformation. So we discussed that actually we don't solve the proper nonlinear transformation, we only linearize, right? And that means that there's going to be some problems later that we are paying for this. If we are not far away from linearization, it should be fine. If not, well, let's say that some error will, non-desired error will just accumulate. And then we discussed a little on Gaussian visualization and sampling. So do you remember this problem? We were just making use of the previous properties on the affine transformation and, well, some prior distribution, right? Remember that we were always using kind of the identity being the covariance, right? So we discussed on this. The only thing we needed is to solve the inverse problem, and for that, we made use of the Cholesky decomposition. And then this is lecture 3, right? We defined a joint Gaussian distribution. In fact, any multivariate Gaussian can be a joint Gaussian distribution, right? We just need to break down the vector into parts, let's say A and B. And then inside, we are going to find this structure, right? There's going to be a vector corresponding to the mean, and there's going to be a matrix corresponding to the covariances. Each of these blocks is, as we discussed last lecture, it's important, right? For the case where the cross terms are 0, right? This corresponds then to uncorrelated variables, and for Gaussians, we also know that that means independence. But that's not the interesting case, right? So the interesting case is when usually these cross terms are not 0. Usually. Okay, and then for this, after doing many manipulations, did some of you try to go over the manipulations again home? You did? Was better when you were alone? Not with me or not with class? Yeah. Yeah, so I think it was detailed enough. I think all of you are welcome to do the derivation if you want. I think others did it here. But at the end, the two results that we obtained were the following, right? So the first one is what happens when we condition this joint Gaussian distribution this way. So now we can assume that xb is given or observed, or we simply know it, right? So, so when this happens, we basically have still a Gaussian distribution. This was an important result that we obtained on Thursday, right? And then the mean slightly changes, and the way that it changes, it depends on the cross terms. Right, and this is another very interesting part, right? So there's here a correction. Actually, we'll formulate, so this is the innovation vector. Basically, it's how much the observation is far away from the mean. And basically what it's saying is that the mean for this condition new distribution actually depends on what you're observing, right? So it couldn't be any other way. They are not independent, so they must change, And then there was a covariance term. And again, there's a formula for this, but the important part is that this was also known as the Schur complement. And then there's this very interesting thing, right? There's a contraction on the covariance. So we have this term, and this term, right? And a contraction on the covariance might look like dangerous, so what are we doing? Like defining a negative covariance. It's not happening, right? Because by construction of this problem, but basically the covariance was reduced. So that means that we are more certain of what is going on. And it also makes sense, right? Because we're observing something not related to A, but let's say we are observing B, and just because there are cross terms, this should give us like some information. So this was the intuition, right? Regardless of the formula, the thing is that the condition variable actually gave us like a little improvement. And then there was this second example, or the second derivation that we did in class, which is the marginalization. So remember, when we talk about marginalization, simply another explanation would be taking out those variables, right, that in this case we are kind of weighting, or weighting with respect to the probabilities. We are just calculating like a new distribution without these variables that we are marginalizing, right? So it's some sort of removing them. This is also equivalent to this, right? So we could write like the joint distribution as a condition distribution, which we have obtained before, and then this distribution. I didn't prove this, but you have this on Barfoot's book. I think I put you the note, and both of these things are Gaussian. So the interesting result is, regardless of the cross terms that exist between A and B, the marginalization, it was simply this, right? We just took the subblock corresponding to A and the subblock corresponding to the covariance A. And we were actually we were solving this integral, and then we were completing this square. Do you remember? It was a long derivation, but the important thing is this. So no matter what you do for covariances, when you marginalize other variables, the right result is just take subblocks of matrices, right? And this is very fast. So this is what you should remember. It doesn't matter if you solve like properly or numerically this integral. At the end, for Gaussians, and that's why Gaussians are so convenient here, this is very compact and very efficient way of marginalizing. For other variables, it's complicated. It's much more complicated. Okay, so this was the yesterday, I don't know, Thursday and Tuesday. So on these two lectures, we were describing, like, I think, the basics for what comes later. And now it's going to be, so all this is going to be useful for the following term, right? It's called the Bayes filter. And this is basically a general form, right? So you will see why this is called actually the Bayes filter. Okay, I think I'm going to move a little. Maybe it helps, maybe it doesn't, but it was moving a little strange. Okay, it works. So we are going to obtain like general form just from a Bayesian definition. You'll see that this is very general. It applies to any distribution. In practice, probably not all distributions are fitted for the Bayes filter, just for very low dimensions, but we'll see what we can do if the distributions are Gaussians, right? So, yeah. Okay. So let me define now like some terms that we will also need. I think I have talked about them like in previous lectures, but we'll need them like specifically because our problem now it's going to be a little more well-defined. It's not going to be so general as, well, any kind of distribution that you have, but we are start introducing like some nomenclature, right, that we'll be using. And the first one is this, observations. I think I discussed on this the first lecture, but today you will see like this a little more in detail. Oh. Right, and this could be obtained from sensors, from other information, from other devices. It doesn't really matter, right? Basically, we are obtaining information from the world. This is a new term that we are going to introduce now. You can think about this as also a way of observations, but in this case, we are going to make a difference. You will see this more clearly in the next lecture, but just let me introduce now actions. Right, so what's the difference between this and just raw observations? The difference is that actions actually change the state of the world, right? So remember, we were defining the world just to be a vector of any dimension, so it's not really like a broad change, but this can actually be just understood as anything that actually is changing your variables, your world. Well, that depends on the representation you choose for your problem. Change the state. Okay, and finally, we should talk about states. Okay, and in this case, this is our world representation, right, or robot representation. That depends on you, right? That depends on the problem that you have. But in this case, let's talk that, yes, this is the robot or world representation or your system representation, right? There's here, yes, you have a lot of flexibility. This can be anything. Okay, so what these state variables, I think, are clear. Now, since we are always talking about distributions, let me also introduce like a sensor model. Basically, we need distributions that are capturing these variables, right? So in this case, the sensor model refers to this. This is the distribution of the observations that we should be seeing, but in this case, with respect to the state, right? So again, on next lecture, we are going to define exactly what this distribution is, right? It actually comes from the observation function, right? That is just relating states with observations. We will derive a probabilistic model, don't worry. But let's say for now that we have this sensor model, right? Just this distribution of observations. The second one is the action model. Right, and you will see a little more clear when I said change the world, right? So change the world in this case means this. We have a previous state, in this case t-1. This is given. We also have an action, and then basically this action model, what it's saying is that what is the distribution of the state after applying this action? Right, so we'll see that for non-trivial systems, these two variables are not the same, right? If they were the same, what are we doing? I mean, it will be trivials, but usually the world changes, right? Like, I don't know, cars keep moving, balls fall from the ceiling, or, I don't know, the temperature grows up. It's growing, right? Because we have our heating like working like 100%. Okay, never mind. So the state changes. That's something that will be interested in modeling correctly. And then out of this, right, so we are going to define like these two models, but there's going to be another important definition in this section, which is belief, right? So what is going to be the belief, right? In this case, it's going to be the posterior of the state. This is basically after using all this information, all this action that we know that has been executed, and the observations that we have seen. There's a question here? No. Okay. So posterior of the state. So let me write it like a little more properly this, right? We are going to refer to this, to belief. This is going to be useful now for the Bayes filter, but in general, this is what we are interested, not our prior distribution of the state, but actually the posterior, right? After we are adding all these actions or observations, right? So it's going to be this, the distribution of this. Here, nothing new, but then basically it will depend on the first action, first observation, and then basically all this chain of actions and observations until we get to the current time, right? So because this is a long list, right, this T can be long enough. Let me just write like a little more compactly, and I'm just going to introduce like a notation that we'll be using later, right? Here I'm going to use the following, right? So we have these subindexes, U from 1 to T, and then observations also from 1 to T. Okay, so on what? For now, on this definition, no. Right? Let's say that you don't care about your previous state because the state has to be estimated. So just purely defining what is a belief, it only depends on the actions and the observations that you get. We'll see that actually, yes, there's going to be a dependence on X0, but just for the definition, let me put it this way. Okay, and I'm also going to introduce like a graphical model just to describe this long chain of actions, observations, and states, right? Because this will help us to understand exactly what is the topology of the problem, right? So in this case, the graphical model, it's kind of a long chain, let's say, right? It's true that we start with X0, and then basically here, so we put here all state variables. Let's say that xt minus 1 will depend on the action at t minus 2 and the observation right. So this is just well, a directed graph. We'll see that there's better representation actually for our problem, but this will be lecture 10, I think. Well, we'll be using factor graphs. But let's say that just Bayesian networks are good enough just to define the problem, right? So then this is it, right? So we have state xt minus 2. It depends on the action and the observation, and it also depends on the previous state, whatever it was, right? And then after doing some calculations, we can obtain like the next state, which will also depend on t minus 1 and z t minus 1. And then, well, the same happens for xt. Right, so you see it's a long chain, every time just defining which are the variables that are conditioning this. In this case, well, I'm going to write it this way. But all these, let's say, dark, they are simply observable variables, while xt are latent variables. We cannot observe these directly, right? So that's why we are defining all these terms like belief and these things, because if we could directly observe the state, that's problem solved, right? You just observe it, and you don't need these other terms. But in this case, we cannot really observe this directly. Okay, so, you know, it's better not. And then let's go to an interesting, yes? Yes. Well, but our belief is just the estimation of this real estate, right? So this is the best we can do. We can estimate this state, but I'm not doing any distinction between belief and state. They are the same thing. The belief is just our best estimator, right? But this is not observable. So it's the same random variable. I'm not doing like any trick on changing names. Okay, so we have this, and then there's going to be another definition that we are going to say that our state is complete. Right? Or we can also call this the Markovian assumption if the following properties are met, right? Okay, so you remember before I was just writing this belief as a long, well, not exactly this way, but this is not the belief. This is just the transition model. Right, and basically, yes. X. It's your state variable, whatever it is, right? But it's basically the vector that you want to estimate. In this case, the actions could be like you are moving, right? If you could somehow know how much you are moving, that will be your actions here on you. You also have observations. In this case, you could be using like GPS measurements directly, or draw measurements from GPS, whatever you want, right? And then build your complicated model. And then you need to decide which is your state variable. So maybe the easiest state variable for you is X, Y, Z on a frame of reference like Earth-centered, right? So that will be your state variable. So that means that after moving, right, obtaining like how much you're moving and observing what the device is giving you, you should be giving your best estimate of this state recursively. Okay, so yes. Yes. Yeah, this was actually his question, right? So he was saying, why are you not including X0? Actually, yes, what we need is a prior, right? We need to start with a prior. I didn't include this on the belief because I was just defining like belief is based on all the observations that we get. But actually a prior, we need to do an assumption for that to be a prior, right? So that's what it was a little tricky, but in fact, yes, you need to start with a prior of this, which will be given. It will be part of your problem, or maybe you also need to estimate what is X0, right? This is also a distribution, so there's going to be a covariance here associated to x0. And then from this, if you keep propagating, like doing the best you can with the base filter, we are going to explain it now, but you do the best you can with the actions and the observations, you will end up having something like this, right? So it will depend on all the previous states that you have calculated, all the previous actions and all the previous observations. Now, as you can see, this grows like unbounded, but here comes to rescue the Markovian assumption, so Markov properties. I'm sure that most of you have heard about this, so we'll say that X is complete, right, if it only depends on the previous state. So in this case, there's this long dependence, but with Markovian property, we can just write it the following way. So it will depend on the previous state, and it will depend on the action, which is the only thing. Notice that here I'm not observing z of t, right? This is just for the transition function. And basically, if you come here, yeah, right, it's kind of saying this, right? So this is only for the motion model, right? If it was like for the observation also, but there's like a little difference here. Okay, so my Markovian properties, they are not, I mean, is this clear? Because this is a kind of an assumption we are doing that is going to simplify a lot the calculations, but is it clear? So in this case, your problem from the GPS, right? So what will be Markovian? It doesn't matter where you were like 1 year ago or 5 minutes ago. It only matters what was your state estimation like right before, right? So it's kind of, you are aggregating the story of all the observations into your previous state. And that's all you need to do the estimation. If that's not true, if you need more observations, that means that your system is not Markovian, right? And then you cannot really do these assumptions. But for now, let's say that, okay, we have a Markovian state. Yep. Yes, I did this on purpose because we don't have the observation at time zt, right? So no zt, right? So that means that this, by Markovian assumption, ct minus 1 is already here, is already accounted when you are estimating the state at xt minus 1. So when you want to estimate xt, this xt minus 1 is really not affecting this, right? So you see there's no direct relation. This part is still missing. And I said that this is just the motion model, to give an example. But if it was here included zt, yes, of course, it should be also. Don't we need an observation of what? You mean a prior? No, once you have defined your state estimation on the previous state, this includes your prior at x0, all the z observations, and all the action observations, right? So no, you don't need it. You just need it when you are calculating the new state, right? So if you see the only connection, according to the graphical model, that's what I said that this is useful, right? Because you can see like clearly on a nice drawing what's going on. There's no direct relation. There's, let's say, a second neighbor, but this is already accounted here when we are doing the estimation. Again, if things were non-Markovian, then we'll see like more terms there, and things will be a little like larger to write. But once we have this property, things simplify a lot. There was, yeah. You say it's complete, X is complete. Yes. So what do you mean by? So here I'm referring to X is complete on the if the Markovian assumption is met. This is our definition of complete here. You just need the previous state to characterize completely the distribution of your, in this case, 60. This is the definition we are giving here. I'm not entering in what is complete or not on classical definition. So, but basically it's this, Markovian assumption. I mean, what the Markovian assumption is clear, right? So you need the previous state. This is the, here, the property that we should be following. Okay, well, so now let me write it for the observation, the same thing. And in this case, we are not assuming anything. Right, we have here all the previous observations and all the previous actions. So again, if there's like, I mean, if we follow or we assume that X has like Markovian assumptions, also Z, then we can write it this way, right? So this distribution of observations only depends on the current state. Okay, so let me go back to the initial definition of belief. You have a question? Oh, okay. Right, so this is how I define it before. So it depends on all the previous actions, and it depends on all the previous observations. Okay, so what we are going to do now here is apply the Bayes theorem. Right, so in this case we're interested, so this, let's say long sequence of observations, you can assume that this is a joint events, right, or joint random variables. We are just interested in the final one. So in this case, we are going to write it this way. Right, so that means just for the Bayes theorem to hold, so we need this way, so xt comes here, we apply still, I mean, it's still conditioned by all the actions, and now it's conditioned by all the observations except this one that we have just, well, let's say change here, and then we have this, right, so I mean, we have a lot of terms here, but this is just Bayes theorem with conditioning random variables. Okay, so. And then there will be like there will be a term which doesn't depend on X, so let's say that what was dividing on the Bayes theorem, we're not interested. This is just a regular normalizing variable, right? So I'm just going to write it this way. Now let's apply the Markov property, right? So as we have just described, if we have here Markov property, we'll have the following expression. So this observation here, all these observations conditioning the ZT, right, become this. And then the distribution for the current state, well, for now it doesn't change. Okay, so we are just applying these properties that we have described. Bayes theorem from lecture 1 and Markov property. And then let me use now the total probability property, right? And I'm going to write it like in a second what it is. So this first part, remains the same. We just have here a condition probability based on our state. And then the total probability is going to be saying something like this, right? So in this case, we have our state variable. And we are also going to account for the previous state. Okay, it's not the best thing to write points. So we have this joint probability, current state and previous state, and what we are doing here is just marginalizing over previous state, right? So you will agree that here we are not doing anything different, right? So this corresponds to this, right? This will be simply a posterior, right? But here we'll be accounting for all the previous states. That's why I'm not including 0 here, because the trick for make this recursive will depend on this step. So, okay, clear, right? Yes? You can, but for now, it doesn't hurt, right? So you can always apply. If you assume that your state variable is Markovian, you can apply it later, right? So I'm not saying anything. It will not help us. In fact, yes, it will hurt. So we will just maintain here these terms. In this case, for the observation, it's here, but for the, well, this kind of transition model with more terms, we are going to just keep it this way. Okay, so what else? I'm writing here this joint distribution, but actually we can just write the same thing but condition, right? So let me write it this way. So this is a joint distribution. We are conditioning by the previous state. You know, I'm just going to put it something like this, okay? And yeah, so this theta actually includes all the actions and observations, okay? Just for me for grading, but if you see on your notes, you will see that, well, there's the other variables. And then just for this to be true, we need to put it this way, right? So we still need like this distribution for xt minus 1. Okay, and then there's going to be an interesting thing to note, and it's here, this point. So this is the same, this is the same. The only thing that I'm going to change now, it's going to be this, right? So this distribution, it's not exactly depending on all these variables, all the actions from 1 to t, and all the observations from 1 to t minus 1, because actually you don't care about the action at time t, right? This is the previous state. You cannot really predict, or here the future action is not going to change your past state. So let me rewrite it this way, right? So this will only depend on the actions until t minus 1 and the observations until t minus 1, right? And then here we have the xt minus 1. Okay, so here the only thing I'm saying is, okay, so this distribution does not depend on the future action. This is totally independent, right? So we know what conditional independent variables are. So we rewrite it this way, and if we do that, then basically this term becomes our previous belief. And here we have our recursive form, right? So I'm going to rewrite it everything again. So we still have this marginalization. And then here, yes, I'm applying Markovian property, right? Because at this point, it makes sense. So this distribution, this is the motion model, will only depend on the action and the previous state, right? It doesn't matter what other actions you have executed or what other observations you have seen. All of them, if the state is complete, should be like captured by these conditioning random variables, no others. And then here, we just have this. Okay, so we got it. This is the recursive form on our Bayesian filter, right? We just derived these equations. What is a recursive form? So for the next iteration, we just need to calculate our belief here. And this is going to be the belief for the next timestamp. So then it's going to be included here. And then we need to do these two steps. The first one is a marginalization after. So we are going to marginalize against these two distributions. And then we are going to multiply by this conditioning, by this distribution of observations given our state. Okay, so these derivations, you can redo them at home if you want, right? It's simple, and the steps, I think, are well indicated. Yes? If I can clarify, why do we have this? The integral. Because you want to marginalize, right? This is what we did here. This is the total probability law. Here, this distribution doesn't depend on the previous state. This was our definition of belief. Right? But in fact, it depends on the previous state, and it's going to be very useful if this has Markovian properties. So that's why we are using the Markovian, the total probability. We are just defining a joint distribution between the current state here, and then we are also doing this condition distribution with the previous state. And if you marginalize this, we know that this should be equal to the P of xt, right? So we are not doing anything. This is just the total probability. Here, there's no assumption. This holds for all distributions.
My question was, why is the last row
Here.
No, last row.
Here. Yes.
We have integral, and we have last row.
Here, last row.
Why the lowest symbol on this board is xt minus 1? The lowest symbol. The very
This.
Even.
Yeah, so okay. So here what I'm saying is that the range for integration is all the space of xt minus 1. But if you want, you can remove it.
There should be symbol for the domain on which the xt minus 1 is defined.
Okay, so you want to define exactly the range of integration, right? I thought it was clear, but yes, you can define in your notes what is the range, and you send it to me, or even better, you can share like this with all of us in Canvas or in Telegram, and then we'll have like, no, honestly, these details are important, I think. So let's define it better. Okay, so I'm gonna remove it until we have a good version of it. Okay, so let me recap like all these derivations, right, in what is the Bayes filter algorithm. Because this is the, well, I think the important result after the derivations, right? Oops. Right, and I'm gonna write it this way. I'm gonna like divide the previous result in two steps. Oops. The first one, it's gonna be belief with a hat bar, right, of xt. What this means is that here, right, we are just referring to this part, right? So that means the belief, just considering the action state, not the observation, only the action. Okay, here you see there's no observation from previous. So, well, actually I'm writing it this way. So we have this way. And this is our previous belief. Okay, maybe with capital letters. Okay, so just intermediate step, we'll call this just the belief from the action that we are observing. And then there's going to be the as we have properly defined the belief, right? And in this case, this belief, it's going to be the, including all the derivation that we did in the following way. Okay, so I'm just substituting. I'm just like all this integral here, I'm just calling it like belief with hat, or hat belief. Yes, so the intuition is that we are dividing this in 2 steps. This line actually corresponds to 2 steps. The first one, it's going to be a marginalization with respect to the action. So we are going to see how our state changes with the action without taking into account the sensor model, right, without taking into account observations. And the second one, once we have obtained this, let's say, new distribution of the state according to the action, it's going to be refined by an observation, right? So the distribution is going to be changing slightly. That's why we have 2 steps. You could be putting this into a single line. But I think it's easy to understand that first we execute an action, and then just because we are considering like things this way on this derivation, then there's the observation that we are adding. And we know what happens when we condition a variable, right? So things change slightly. Okay, so, and then I said that this was actually a recursive form, right? So what we do is we have a prior. There's going to be an initial prior, right? Belief of x0, if you want. And from this, it's going to be always the same. So we use our prior, our belief. In this case, we have the first step, which is the marginalization, right? It's only taking into account actions or the next action. Then we'll have our belief bar, right? And then the second step is, okay, so once we have calculated what is going to be the distribution according to this action, how we are changing the world, then we observe it, right? And by observing means this, right? So we get observations, and this is going to change slightly the distribution, right? So it's these 2 things that is always happening in this recursive form. You can put this on one single line, considering both at the same time. But in this case, also a nice property of this Bayes filter is that this is divided in 2 parts, right? So first, as we have defined, we only need the action, right? So this is, let's say, considering all the previous states and doing this some sort of weighted average, which is the marginalization. We take away the previous state. And then the second one is we observe, right? And this observation is going to change our result. Okay. Yes. 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 If you calculate the posterior of this, why a joint distribution? Yes. Yes. You have a joint distribution, which you are marginalizing. And so that's why we spent like so much time yesterday. You will see in a moment, but that's why we spent so much time on Thursday explaining what can you do with a joint distribution if you marginalize it, right? Yeah, no, this is just, will be exactly as you said. You can define this as a joint distribution. There's going to be like some things not really, we need to change a little detail to make this a proper joint distribution, but yes, in fact, the way of solving this is going to be consider this a joint Gaussian distribution when we start talking about Gaussians. The important thing here is that this is not Gaussian. This holds for every distribution. For now, this is just the Bayes filter, right? Any distribution could be plugged in here. But I think you are advancing a little the material that for Gaussians, it's going to be a little different, right? It's going to be very efficient, the way of calculating this. Okay, well, thanks for the comment. We'll discuss it later a little more. I had here some example with actually what is marginalization in action with some rectangular distributions or uniform distributions. Actually, I don't think that there's a need for us to do it. You have these nodes in Canvas, and you have them in GitHub, right? So as a result, well, basically you will see that this operation is very involved. Is it similar also to a convolution without doing the negative, right, of the signal? But in this case, we are just giving symmetric distributions, at least from some point. And then the result is going to be that not every distribution that you want to do the okay, let me write it this way. So in this example, this is a rectangular distribution, and this is another rectangular distribution. And as a result, what we get is some sort of trapezoid, right? So imagine you do this multiple times, and you don't know what's going to be the output of this distribution. For doing this, you need to solve this integral. And that can be expensive. And then basically the question comes, okay, so you're not going to be solving for this. No, we are just talking about the integral, right? Imagine about the conditioning. But actually, the good thing about Gaussians is that we know that if we marginalize two Gaussians, or a joint Gaussian, if you want to name it, we are going to get as a result a Gaussian distribution, right? And that doesn't happen for all distributions. In fact, that's a very rare thing, right? So on this example, you will see, okay, so you can make it if you want, but it's more visual, right? So the problem is exactly when you don't have like a prior that is Gaussian, and in this case, this is a transition or a motion model. This comes from the transition function. When we don't have a motion model that is Gaussian as well, the result is going to be unpredictable, right? So you basically need to calculate this numerically, or maybe you are lucky and you have a closed form, but it's not always possible. With Gaussians, we know that this happens. So we have like a product of Gaussians, and we are going to get as a result of doing this marginalization a Gaussian, which is very easy to obtain, right? Remember, it's just taking a look at subblocks of matrices. So, well, I guess this is a good point to start saying, let's do the assumption of saying that our prior is a Gaussian distribution, and then this is the only assumption that we need to do, our prior to be Gaussian. And then all the transition functions, which can be linear or non-linear, right? We are going to build a probabilistic model from these functions, and we are just going to make them Gaussian because the prior is Gaussian. Right? So in this case, we are just assuming this to be a Gaussian distribution. It's going to have like great advantages. The only outcome is this, that this is a strong assumption. Right? So it's basically a unimodal distribution, and well, there's other things. But in practice, at least for the Bayes filter, this is going to be very, very efficient. Okay, any more questions? So the important thing from this first part of the class is this recursive form, right? But if you don't have any questions, we will move on after the break, and then I'm gonna start defining more interesting things that we can do this. We can make use of the Bayes filter for the Gaussian case. Okay, so 5 minutes, 8 minutes. Yeah, 8 minutes. Okay, so we have discussed what the Bayes filter is. Now let me introduce the Kalman filter, and I guess this is something known for most of you, right? So you have heard about the Kalman filter, maybe you know the equations. So I'm going to describe a little what it is. Basically, well, this is meant for dynamic systems. Basically, that's what we want, right? Systems that change over time. We will be observing it, and there's going to be like changes in these states over time. So this is great, right? So far, this is similar to what we have discussed. And then the idea is going to be a little different than usual. So we are going to do a derivation from the Kalman filter directly from a Bayesian approach, right? So on the Kalman filter, there's a lot of discussion on optimality and all this. But for this derivation, we are going to be using just a Bayesian approach. And we'll see that we'll get exactly the same results, right, as you can obtain after doing many optimization steps. Okay, so I'm going to write it now. Obtain from Bayes filter. And then we already discussed a little about this, but then basically what we need to assume is that we have a prior that is Gaussian, right? Yes.
What is the first word?
Obtain. Yep. Assumption. Prior is Gaussian. Okay. So I think now that we know this, we need to define exactly what we meant by this. We are going to describe a linear dynamic system, right? So in this case, let's write it this way. So we have a state transition function. Okay, for instance. So, yeah. And in this case, it's this, right? We just have a linear function that is, as I said, changing the state of the world. This matrix can change, so that's what I'm writing here as subindex, but it's linear, right? And then we have the same for the action, right? It's also going to affect how the state changes. And then since we are also interested in, well, let's say that this system is not perfect, right? There's some randomness here, not just because the state has, is a random variable, but because, you know, when you change things on the wall, there might be like some perturbations. Not everything goes as you expect. So we are going to assume that there's also another random variable, right? And in this case, xt is a zero mean Gaussian distribution with covariance R, right? So what it is, this is basically a linear function. You have a question. The prior is, as we said before, the state variable at x0. This is what you need to start doing the derivation of the Bayes filter, right? Or all the others, like observations and the actions that you're executing, we are just assuming that there's like a distribution for them. But the only one that matters is this, because on the recursive form, when you see the belief, right, the only distribution here that you need to have information and do some assumption is this one.
How is it random with
No, it's random, but what you're assuming is that this distribution is just a Gaussian distribution. For the transitions, we'll see what's going to happen. But what we'll have is usually a nonlinear function. And then we have discussed what you can do with nonlinear functions when you have a prior that is Gaussian, right? So you will basically be linearizing, and the result of this distribution is going to be Gaussian, right? This is going to be explained next lecture. But for now, on this general form, we just have a transition distribution here for the action, and then also an observation distribution here, according to the previous state. So far, we are not saying anything about Gaussians or what is these distributions. It's going to be later. OK. We can discuss it later if it was not clear. But so the Bayes filter is clear, right? I mean, is there like any question? Now we are doing these assumptions. But before on the Bayes filter, we were not doing any assumption, only Markovian properties and applying probability properties, right? Now, this is where we start like doing the assumptions, right? And this is the first one. So the prior is Gaussian, and the system is linear. These are the two assumptions. Oh, it's not moving well. Okay, no other assumption we have done. Okay, so, no question, okay. So as I said, we have a linear function plus a Gaussian noise. Right, so then we know that if this is Gaussian, this is our first assumption. This is not going to be a random variable. This is just, let's say, some variable that is given. And this is also a Gaussian distribution. This is a linear system. So we know that xt is going to be Gaussian as well. Right? We describe this. This is basically the affine problem, but instead of one random variable, we have two of them. Right? So this is also going to be a Gaussian distribution. Is Gaussian. Okay, and now let me write it a little more clearly. What are all these variables, right? So in this case, we are going to have like different values for xt, right? So in this case, the dimensionality we don't know, but well, we know, right? And in this case is n, right? So we have here in this state variable and different components, right? For the action, it's not necessarily the same number of variables, right? So the dimensionality here will change, and actually dimensionality is m. Right? And, well, what else can we say? We have here matrix multiplying the state. So this should be square, right? Right? So it's, I mean, all the parameters here are n by n, right? So here n, well, doesn't matter. And then the same happens for b. So let me write it just here, b, right? In this case, this is not square, at least not necessarily. But, well, the matrix that we get is this, n by m. Okay. And, well, the same happens for the observation function. We are also going to define a linear observation function. Right? In this case, it's the following way. So we have, again, a matrix multiplying this. The dimensionality of set has not to be exactly the same as the dimensionality of our state variable. And then we are adding some Gaussian noise, right? In this case, why? Because the observation might be noisy by itself, right? It's not that we are just accounting the uncertainty on the variable x, right? But there's also like other uncertainty that is not quantified on this linear system. So we need to account for this, and in this case, it's going to be the same Gaussian variable with zero mean, right? And in this case, the covariance is q. Right? So again, linear function. This is the easiest system that we can describe, right? Just linear things. Nothing from this, we'll see that this can get a little more complicated, but I think this is the first step, right? And then we have a Gaussian distribution, a prior that is Gaussian, right? So that means that Z, it's also going to be Gaussian, right? As we define, so when we do a fine transformation of a Gaussian variable, and then we have a second Gaussian variable, we are just summing, this distribution is going to be Gaussian. Okay, so let me write again the structure of these set variables. In this case, the dimensionality of set is k, right? And that means that the C matrix, well, we can just write it. It's k by n, right? So this can be square, maybe, if k equals n, but usually we might observe less things. Or yes, and then q, it's also our covariance matrix. We know that it's q, k by k, right? So this is nothing new, just because here the dimension here is k. Okay, so from this, what we can do is we can create, after knowing all these facts, that the system is linear, the observation is linear, our prior is Gaussian, right? And then we have other Gaussian variables there, adding noise. We are going to be building what is actually these distributions, right? So in this case, what is the measurement distribution? The same goes for the action distribution. Okay, so the system is linear, observation linear, clear. Okay. Now I can give you just a very simple example, right, of what we mean by just a linear system. In this case, we can say that the temperature system, right? In this case, X is the temperature, right? Could be in degrees or whatever you want, right? Our action space can be, in this case, we hit on or we hit off, or maybe we open the window or something like this. But let's say that this is a discrete space of two actions. Okay, and then we can have a linear system, right? We are not sure exactly what they are relating, but let's say that the system changes linearly, right? And then there's like a part that depends on the action that we take, and then there's going to be a noise. So this is what we are saying. In this case, maybe the system just decreases the amount of heat, right? Because let's say that outside is cold, here is hot, so that means that some of the heat gets away, right? So this A should be smaller than 1, right? If it's bigger than 1, that means that our system is kind of growing in temperature, but if it's smaller, it's every time a little less, right? Yes? So if we do nothing, if we don't hit this whole building, it's going to be colder, right? So just the state transition of this, let's say, system is like decreasing. But still, we can say that this is Gaussian, this is linear doing this broad assumption. I'm sure that there's like more equations there that, well, can complicate it. And then we have an observation function. And in this case, maybe the observation function is not really like degrees directly, but we're observing volts from some device, right? So this device is going to be noisy. That's why we are including here like this noise. And then, yes, so set, it's kind of volts from sensor. Okay. So, well, in this case, then C will be something like this. So it's a simple system. You can imagine any other kind of system. It can be as complicated as you want, right? We'll see later that systems that are linear are very strange, but the nonlinear case, it's also going to be like interesting for us. Yes? This? This is just, for example, an example. Yes, example of decreasing temperature. So if you think about it, every time that the system transitions, you are losing heat. So this is what it means. It could be the same. I mean, if we were like perfectly isolated, this could be 1, right? And that means that we stay exactly the same. So this system doesn't change. But there's noise, and then there's actions that we can do. So it's just an example. Basically, deriving these equations is the second part. What we're interested on now is saying that this is linear, priors being Gaussian, and then we'll see how all these distributions are expressed. Yes? These are the units of C. So if you have here volts and your state are degrees, this is the units that you need for this constant, right? Okay, but this is just an example. The important thing is that linear system, right? Anything that simply changes and you can observe. Okay, so I'm going to write now the equations for the Kalman filter. I think, who has already heard about Kalman filter before? Almost everyone, right? But did you derive it? You did some derivations from a book. So, okay, that's great, because we are going to be doing this from this Bayesian point of view. So you will see that things are very clear and very straightforward. But just as a reminder, so what is a Kalman filter? There were a bunch of equations. Kalman filter, so this is the linear case. There were like some equations, but you will see that there's actually no need for you to remember, right, as long as you understand what's going on, right? I think this is the important thing from today, understanding what's going on, what each of these equations mean. Okay, and as we said, so the transition function is linear. The observation function is linear. And priors and this noise that we are adding to the system is Gaussian. Right, so this is all we need after we have defined all this. Okay, so if these conditions met, we have linearity, and then we have all these. The Kalman filter gives us the best unbiased estimator that is possible to obtain, right? So actually the initial derivation was after doing some optimization. Basically you are saying, okay, what is the best estimate of our X variable that we can do, taking into account all these facts, right? So Gaussian distributions and this linear system. So it turns out that it's optimal and it's non-biased. And well, this is also, just for you to remember, like this is the Kalman filter is blue, right? And this stands for best linear unbiased estimator, right? So if things are linear, priors are Gaussian, the best thing you can do is the Kalman filter, right? There's a derivation proof, many papers over the years. What happens? The world is not linear, so that's our problem. And maybe distributions are not Gaussian. So, but still, I mean, this result is quite best linear unbiased estimator. Okay, so maybe this is what you know from the Kalman filter, right? Previous knowledge, so you know that this is the optimal estimator. You have used this in many cases. I'm going to write now the equations, and I'm going to reason a little what's going on. So maybe some of you already have like a hint of what's going on, but we'll see. Again, remember that this derivation, our derivation, will come directly from the Bayesian point of view, right? So, and the optimization, that's the maximum posteriori, and this Bayesian derivation are actually the same, right? Just because, well, this is linear. If it's not linear, then it's not the same. I mean, the results will be different. But in this case, they are, right? So we are just going to take which one? The easiest and easiest to remember derivation for this Kalman filter. Okay, so this is the first equation. Again, we are going to derive each of them later. We have the second equation, right, which is related to the covariance. We have a third equation, which is called the Kalman gain. That this one might not be as straightforward as the other two, but still, today we are going to derive it. And then new mean. This, by the way, this difference is the innovation vector, this set minus what we'll be seeing, and then covariance. Okay, so I don't remember these equations. I usually have to take a look, so the same is for you. It's more important for you to understand, right? So this is my objective. I don't want you to remember this. In fact, you are allowed to use like paper of sheet in the exam if you want. Now, understand what's going on. I think this is the important part of the lecture. So, well, and then we have this. Okay, so now what I'm going to do is kind of break this down again into these two steps. That's why before we were defining like 2 steps. Why not to do the why not to do the base filter in just 1 step and put everything there? Because sometimes interpreting things is important, right? So you get this intuition if you break these things sometimes in smaller parts, if it's possible, right? So in this case, we have the first 2 equations, right? And these 2 first equations, we can actually say that these are equivalent to our in our base filter to the prediction. And we will see in a moment that actually this is the belief of, as we have defined it, right? So this is going to correspond to the marginalization of these joint variables, right? So we'll see in a moment. Okay, wait. So this conditioned by U1, D, and then Z. Well, conditioned by and we'll see now what they are, right? And then we have the second part, which should be what? Like we are considering here observations, right? So in this case, if we consider here observations, that means that here, if you see, this is the only part where we have an action, right, in these two equations. Later, it doesn't appear again, right? So this is giving us like some hints, but on the other side, here, what we are doing is considering the observations, right? So you can think about this as a way of doing the correction, or update step, which is doing that, right? So it's taking into account Z. Right, and then, well, this corresponds to this belief, as we wrote before, right, that in this case, and then I'm going to change a little here, and I'm not going to well, I'm not going to take the Markovian assumptions until the very end, and you will see later. But this is just the high-level idea, right? I'm going to develop it later, so don't worry. This is just orientative. But the first part of these equations actually correspond to the prediction. So all we are doing here is a marginalization, right? Taking into account what's happening to our state after applying an action. So this is the first two equations, and the second and the third equations, well, basically, this is some sort of way of grouping matrices, I mean, the Kalman gain, but the last two equations are just taking into account this conditioning probability here that we have here. And this is basically how you are changing what you think that the state is changing after executing an action, after observing something, right? So here we are adding more information. Okay, so another important thing is we'll do that, and then the output of this algorithm, actually it's a belief, right, of xt, and that's why this is a filter, right, because the belief that we have just calculated now, it's going to be used on the next step. And we do this recursively as many times as we want, or as many observations as we have. Okay, so these equations were Kalman equations. For those who said that you remember about this, might be familiar a little, right? But don't worry, because now starts the explanation, right? So now what we are going to be doing is all these things that I'm saying here, right? We are going to prove them, right? So we are going to derive them, and then we'll see that actually they correspond to the same thing. Yes? Prediction, and here is correction and update, right? Yeah. Okay, well, didn't improve much. Okay. I wish I could write better, but maybe I need I want to try with different kind of thickness in my pen. Maybe this improves, or maybe it's just my handwriting, which is not good enough. But, yeah. Okay, so we were saying that we are going to derive all this. So let's start with the derivation of prediction, right? So here, derive prediction, right? And in this case, we said that this corresponds to this belief, right? Okay, I'm going to put here a little color, because, yeah. No. Oh. Okay, so what do we do to derive this? We know that our prior is Gaussian and the system is linear. So as you may have guessed, we are going to be using our favorite tool so far, which is the expectation operator, right? So we know what is the transition function. We know what is the prior distribution. So if you want to know what is the like the distribution for xt, it's just going to be that. So we just use the expectation operator to calculate mean and covariance, and we know that this is going to be linear, right? So in this case, the mean, and this is mean bar of xt, means the following, right? So this is the expectation of our state variable xt, right? And in this case, it's going to be conditioned to all the previous actions, right? And all the observations from time 1 to t minus 1, right? Remember that here on this prediction step, we are not making use of the observation so far. It's only going to be like the final action here. And some of you might be wondering, so why are you doing this instead of if we discussed before that this is Markovian, why are you putting this? Well, it's because there's a little step like later that we need just to carry out all these conditioning variables, and then later you'll see that things work out. But if we assume Markovian properties now, then it's going to be a little more complicated. So we have it here. Let me write it like this, right? So this is, again, like all these conditioning variables. And then, yep. Because no, because belief, we define it on a different way before, right? So what we are going to be using now is create a joint Gaussian distribution, and then we are going to calculate the belief after marginalizing. What we are doing now is we are going to create a joint Gaussian distribution, right? A Gaussian distribution actually that depends on xt minus 1. And you will see this in a minute. So that's why we are calculating what is the expectation of xt, because now I'm going to write this with respect to xt minus 1. And then all the results from the mean and the covariance are going to be depending on the previous state, which is the one that we know that's our prior, right? That's what we know. From xt, we don't know anything, so we cannot do this directly. So we use the transition function. And okay, so at some point I think this is similar to one derivation that we did on Tuesday, right? So A is scalar. We can take this out of the expectation. Xt is known, right? So we know that xt is the mean. Xt minus 1 is the mean of xt minus 1, right? And then what else do we have? We said that in this case we are going to treat u not as a random variable, but just as a number, right? A given number. So that means that constant values get out of the expectation. And then what is the mean of epsilon? 0, right? We define it this way. So this is it, right? So this is the mean of this joint Gaussian, of this, let's say, state transition if we consider the prior. We'll see in a minute that this looks like the first equation, but this is not first equation. And then we also want to calculate what is the covariance, right? So for the covariance, we apply the definition of covariance. So in this case, it's going to be this. Here I'm using the mean that we have just calculated, right? So we do it this way, and remember, we are conditioning with respect to all the previous ones, all the previous observations. So it's something that we can remove at any point because we know about the Markovian properties, but just let me put it like this here. So now what we are going to do is the same. So we have the equation for this xt, right? So we know how this system, what is the transition equation for this system. Actually, it's linear, right? So we write again, at xt minus 1 plus but plus epsilon, and then here we have the mean. Okay, so what is the first thing that we can do? We just remove these two same quantities, right? Oh, wait, before doing this, we need the second part, right, which is going to be exactly the same, but transposed. Okay, so all I'm doing is just removing these terms that are constant, but it's the same thing. And we know that always covariances are like square form, right, of these errors. So we have it this way. Now, let me just rearrange things a little more conveniently. And in this case, we are going to take like all these parameters that are multiplying AT, right, the following way, right? So we have AT here multiplying this and also multiplying the mean, right? And then we have epsilon, and the same happens at the other side, right? So this is the same. Okay, so now we are just going to multiply like each of these terms, right? So all these AXT, all these terms multiplied by this one, right? After taking into account the transpose, so we get it. What we get is something like this. This is like this, by the way, right? And just remember that. Well, there was like some rules that we use for the transpose of two matrices. So you can rearrange all this transpose, right, equals to this transpose and this transpose. This was explained. Yes, this is known, right? Yes? No. It should be. It should be, because this is the mean that we have just calculated, right? So this is the bar, just consider the mean, just considering the action that we are executing, right? So we have this. And then what else? We have all these terms multiplying epsilon. And then we have a lot of cross terms here, which, well, are multiplying epsilon against x in different forms. Right? So first of all, we know that xt and epsilon are uncorrelated, so they will go away. And then we know that mean, which is a constant, is just being multiplied by epsilon, and the mean of epsilon is 0, so that means that this also goes away. The same happens for the things that are on the reverse order, right? So xt minus 1 minus sigma multiplied by epsilon on this side, they are also going to be cancelled. And then, and then we have this. So after doing like this rearrangement, which I think it's, if you follow like previous lecture and this one, we are just adding a little extra term, but it's almost the same. Here what we have is constant matrices get out, and here this is the definition, well, the covariance of xt minus 1, right? So that's why we are writing it this way. Yeah, no, you were right, No, this is not bar. This is the previous mean, yeah, of course. What we have a bar is on xt that we have calculated, where it is. I was thinking, no, this is not good. Okay, are there any other? Second? Yes. No. Now, the only one that is needed is this, because yes, we are writing it this way, and then we are just substituting things. Okay, I think, yeah, now it's right. But anyway, the thing is that this is related. We are just doing covariance transformation. There's this linear function, and then the result is this. Right? And now this is where we build the joint distribution, as we were discussing. So why is that? Because we are going to have this, right? This is the distribution of t jointly with xt minus 1, and then it depends on these data parameters as we defined before. So we know that mean here it's going to be this, right? This is the one that we have calculated, and this is the one that we had before if we were doing this joint distribution, right? So means are this way, and then here for covariances it's going to be the following. So we know that the covariance here is the previous one. This is given. This is our prior, and then this is the covariance that we have just calculated, the covariance of xt bar, right? So I'm just going to write it this way, xt, and then it simply happens to be related with the previous covariance. And it makes a lot of sense because the only thing we are doing is just transforming, right? This previous random variable, right? It's transformed this way, and then because there's the epsilon term, we also have r's, right? And then we know that what we want to do is we want to marginalize this. Right? This is belief hat of xt, right? This is just marginalized. So that means that our this distribution is going to be like this. So for doing this, what do we need? Do we need these cross terms? Are we going to calculate them with the same expectation operator? We can, but we will not, right? Why? Because the only thing that matters for calculating this marginalization is what is in these two blocks. So this is going to be very convenient. Okay. So this block and this block. And with this, we are calculating the marginalization, right? If you expand this, you are going to get exactly the thing that we had before. Transition, basically, the distribution of the transition, xt conditioned by xt minus 1 and all the previous observations, and then our belief. And that's where I'm keeping all these parameters here, because I'm putting here the belief. If you want, you can apply Markovian properties later, right? Once you are inside, but just for building the joint distribution, considering everything, we put like all the previous conditioning observations and actions, we build the joint Gaussian, and it's as simple as this. So we just calculate one of these blocks, and this is not just a transformation. No, what we are doing here is marginalization. So this is familiar, right? If we go to the Kalman, well, to the first two equations, we have these two equations, right? Okay. Yeah, I think I'm not going to go back again. Right? So number 1 and number 2 are the same. And this is, I think this is proof, right? So this is just marginalizing. Yes? Because this is our assumption. if you have a bias, then what you need to include is this bias into your system, right? So what you will have is an affine transformation that calculates for these biases. But in terms of noise, and in order for this to work, you need to have a Gaussian random variable, 0 mean. If not, when we go to this part here, there's going to be a part that it will not cancel. So you will drag all these terms. I mean, you can. Actually, you can. Yes, exactly. So when you come here, right, these terms here, actually, these are not going to disappear because the mean is not 0. So you are going to have like something which is multiplying the mean of epsilon. But again, it's easier just to calculate the bias. Assume that your noise is 0 mean, and then calculations are going to be a little easier if you know that it's bias, right? So, yeah, but a very good question. So if you go deeper into doing more expectations or more manipulations on expectations, you might find these cases where maybe things don't cancel so easily, right? So then you still need to consider, so what's going on? Okay, so this part is clear. Number 1 and number 2 equations. Yes. No, it's not 0. In fact, it's not 0. No. That's the beauty of marginalizing a John Gaussian. You don't care what it's here. Actually, it's going to be something like A multiplied by this, and here I think you have something like this. But you don't care about this. It's totally irrelevant. Cross terms, we discussed last lecture. No, for marginalizing, it's not interesting. So that's what we are doing. We are marginalizing this. Clear? We'll see on the next example when we see the conditioning where actually these cross terms are important. So we'll need to calculate them. Okay, but we are not doing any trick. We are not cheating. Marginalization is exactly this. We are marginalizing. It's irrelevant what these cross terms are. Okay, so now we are going to derive the correction step. Any questions so far? Thumbs up if you are like with this kind of relation between what are the equations and then actually what we are doing, which is very simple, just marginalizing. No thumbs up? I can go back and explain it. No? No? Okay, you're simply tired and you don't thumb up? You have a question or this is... Why do you care? Because if not, how are you going to be solving the integral, right? If you have like two Gaussian distributions, right? You need to set them properly. If you just have a product of 2 Gaussians, in this case, the conditioning transition and your prior, and you have the integral, what is the result of this integral? I don't know. But I know about the joint Gaussian, so that's why we are putting things together in the same joint Gaussian distribution. And then if you see, we are relating the xt with respect to xt minus 1, plus other terms. So this is the way of, if not, it's not so clear. You will need then to solve this either numerically or maybe you have another closed form somewhere. Okay. No. Okay, so I think it might be a little deeper than this. So you are talking about a non-stationary biases, right? In this case, yes, you need to account for them, and you might do like several things. You might assume that biases are another random variable, and then you estimate them, in which case your state variables are just increased, right? Or you can assume that they are constant, change accordingly your affine function, and this will be like a non-proper way, but still, this will still work. And if you want to consider these biases just as part of your noise, then on the equations for the expectation on the covariance and expectation on the mean, these things will appear. They will not cancel. So you will have just more terms. So either of these three questions, of these three solutions you can use. People usually what they do is they assume a zero mean Gaussian noise, and then they assume other random variables because that makes the derivation easier. If not, having these terms will require you to redo all the Kalman filter, which you can, by the way, but it's easier just to assume, to consider more random variables than changing the whole equations. Okay, good comment. Derive. Always try to be lazy. Do the easiest thing, right? As long as it's correct, right? So you care about correctness, but solving the problem, the same problem, just by overcomplicating, and you don't get a better solution, you just get the same solution, but after doing more rounds, that's not giving you more. So try to be like more direct or just simplify. Okay, so I think we still have time for this. Derive the correction step. And as we, this is belief of xt, no bar. Okay, and the process is going to be very similar. So what we are going to do is we are going to build a joint distribution. In this case, the joint distribution is a little different because we have already marginalized xt minus 1, so the previous state doesn't matter. But the joint distribution now is going to be dependent on the observations, which we know there's a function for this, and the current state variable, right, which is xt. And then again, this is going to be depending on xt, all the previous action taking from 1 to t, and all the previous observations. But now we are not including, because t is already here, right? This is the one that we want to calculate the distribution. But these were just given. So it's going to look like this. And then we know that this joint distribution, in fact, it's going to look something like this, right? So it's, if you just derive, like in general, this is the product rule. You do the derivation of this. You get this. And then here, what we are going to get is belief of xt, right? Belief bar. Okay, so the plan, it's kind of the same as we did before. Build the joint distribution. We are going to see that what's in the covariance. We don't know what is the covariance of z, right? We don't know. But we are going to relate it to the covariance of xt, which we know. Okay, so let's go. What is the first step? Calculate mean, right? And in this case, I'm going to write the mean of z. So same as before, we want to condition this by all the previous observations. And in this case, I'm just doing this substitution. Here, there's a linear function relating state and observation, and it's the following. Right? So what is the result of this? C is a constant matrix multiplying, gets out the mean of xt. We have already discussed that with the information we have now, xt bar. The mean of delta, by definition, is 0, right? So this is what we should be seeing, right? It makes sense. So basically, you have an observation function. So what you should be seeing is your mean just being multiplied by the same matrix. Forget about noise, right? If noise is 0 mean, what you should be seeing is just the mean transformed by this matrix. So nothing crazy. Now, let's calculate what is the covariance of z, right? And this might look tedious, but I think the methodology for deriving covariances is useful. So we started with less variables. Now we have more and more. But we can do it. Right, so this is just the definition of covariance. Again, I'm putting here all these conditioning events because later it's going to be convenient, but you can forget about them if you want, just for doing the derivation. And then what are we going to do? We are just going to write what is the value of each of these z's, right? And in this case, z of t equals this. And then what is the mean? This is the mean with bar. Right? And the same goes on the right-hand side of this expectation. So we have Zt plus delta minus Ct. Okay? And now we are going to do a very similar thing. We're always doing the same thing, by the way. But we rearrange things on a way that we can obtain, like, what is the covariance of xt bar, right? So in this case, this means the following. So we have this, we rearrange zt, no, zt. This is another good practice. So if you go home later and then you want to redo some of these derivations, you can. Actually, I think can be a very good practice. And then we have all these terms, right? But it's simply a matter of how to rearrange them. So in this case, we know what's going to be here. Now what else? We have like a term that depends on delta t plus something. In this case, we know plus xt, so we know that delta and xt are uncorrelated, so these simply go away. The same goes for the reverse order. And then we have the square of delta t, right? So this covariance, at this point, I think it should be very familiar for all of you. So every time that we do this covariance transformation, we always get kind of the same thing, right? So the matrix just transforming this space, in this case, we are mapping from state to observations, but in the transition was from the same space, I mean from the action space to action space. In this case, we get this. And then this is the covariance for deltas, right? Q. Okay, so easy. Please redo it at home if you don't see like some of the steps clear, but you should be getting this result. And then, unfortunately, or luckily for this example, we are also interested in the cross terms, right? So for the cross terms, let me calculate them this way, right? This is the cross term of x and z, and then we know that by definition, it should be this way. Or if you want to use the expectation, which is actually what we need, it's this, like x minus its mean multiplied by z. In this case, in this case, okay, allow me not to use now the bar, but actually this is the mean that we have so far, right? So the posterior is just with respect to the action, but this is the best we got here. But basically the idea is this. On the covariance, we are just measuring these errors with respect to what we should be seeing. Okay, so as usual, let's start writing. This is going to be a little more compact because what we want to relate is with respect to xt, right? Everything just related with xt. So this is the first part. I'm not changing anything. And this is the second part. Right? So, okay, if you rearrange these terms here inside, right, all these all these things, multiply by the C, right? And then you put them on the right order, we are going to get the same thing, right? So xt minus its mean, multiply by xt minus mean transpose, right? So the thing that always, the covariance basically of xt. And then we are going to have a C variable, just multiply here on the right side. So what I have here is, okay, no, I'm going to grade everything. Because later we also have like this term, right? Xt multiplying delta t, which we know that they are uncorrelated. And then we also have this, mu multiplied by delta t, which we know that delta t is zero mean, right? So that means that these two things go away. Right, so we got it. Finally, after some derivations, we got our nice result. Okay, everybody agrees so far? Just practicing on expectations, I think it's something good. You should be familiar, you should be proficient. Practice if you feel that some of these derivations you are missing something, but I recommend it. So now we are ready to define our joint distribution, right? Okay, I'm going to write it this way because this can be a little big. So we have, first of all, the variable on x that we know that it's this mean bar that we have calculated before. This is the best thing we can get so far after adding the observation, right, after conditioning. And then we have a mean on the observation, on z, that we just calculated that looks like this, right? This is, we did this like a little up. And then about the covariances, what can we say? Well, the easiest thing that we can say is that the covariance of xt bar, as we have it now, is this one, right? So this block is clear. What is not so clear is that, well, what about the others? So in this case, the covariance of z, we derive it also like just above. We got it this way. So this is a linear system. So that means that we are just doing covariance transformation, right? So this is the covariance for this block. And then we have the cross terms, right? So we calculated for xt, right? So in this case, this is x and this is z, right? So that means that for xz, which is the one that we calculated, should be here. But we know that this should be this must be a covariance, right? And for a covariance to be valid, it must be symmetric. So we just make use of this covariance is also symmetric, and then we just transpose this, right? Because these two blocks should be, one is the transpose of the other, right? If not, they will not be symmetric. Okay. So we calculated this one, but this just happens to be the, this is this, right? Which we know that it's xz transpose. So we know. Okay, so now we have a joint Gaussian. Now I think we are ready to use like this result. And if you remember, what we're interested now in calculating is this, we're interested in calculating the belief, right? So that means that xt, using now the observation, using all the previous actions, and using almost all previous observations, right? And this is what we have defined as belief. So what is the result of this? We know that we have the joint distribution of xt and zt here, right? So we just need to condition xt condition with respect to z, right? So in this case, we are going to use the result that we got from previous lecture when we say if you have a joint distribution, a joint Gaussian distribution, and you want to condition things, the only thing you have to do, I'm going to write now kind of the big equation is this, right? So you just keep, this is the one that we're interested in, right? X, Z, we don't care. It's gonna, we need it, but we don't care to estimate what is the distribution because at some point it's gonna be given. So this is gonna be like a conditioning variable. But in fact, this is also a distribution, right? So it was drawn from a distribution. So the mean for X is this. This was the previous one. And we know that conditioning variables actually are gonna change, right? The mean a little. So I'm just using the definition that we got from last day, using the equations that we got there. Right, we have the inverse here. So this is for the mean, right? Mean, the mean of this new condition, of this new belief, of this new posterior now considering Z, it's going to be slightly changed depending on the Z observation, right? So it's not the same as before, right? The system has propagated according to the action, but now there's like little correction, right, after you observe, which makes sense. And then this is also a result from the previous lecture. What we get is a little contraction on these covariance. Okay, and if you remember, this was the Schur complement, right? So now these are just the results. X. This is, by the way, right? I'm just putting here like each of these blocks. Well, before, right? So now we have each of these elements. Now let's substitute what we have in this joint Gaussian with the values here, and we'll see that actually we will derive like closed form equations for these that are exactly the Kalman equations. So let's go for the mean. Right? The mean after conditioning with this observation is going to look like this. This is the previous one. I'm here now substituting. So in this case, covariance of xz, just following this derivation, it's this, right? Covariance of z inverse, it's this. I think there's an errata on the notes, but you can correct it. And then there's this innovation vector, right, which is the observation that we get minus the mean, right? And in this case, the mean of z is this. Right? I'm just substituting things. So it's like a long equation, but actually what's happening here, that if we rearrange things on this way, all this, according to Kalman equations, this is what he called the Kalman gain, right? So this is the Kalman gain, and this is the third equation. So when I grow it here, but it should be. That was a mistake, so yes, you should correct it on your notes. But there's an inverse. That's what I say that I don't remember the equations. It doesn't matter. What it matters is what you are doing. And here you are just conditioning a joint Gaussian. So this is a good example. I don't remember. I'm not going to ask you to remember. On the exam, you will have a piece of paper to write whatever you want. But what's important is then you need to say exactly where each of these things come from, right? Okay, good point. Now, I mean, it's not that I don't remember, it's now that I don't see it and I write it properly, which is more serious. but you will forgive me. And what? It wasn't? It was, well, it was correct. Okay. Yeah, I guess I forgot, I wrote it. But anyway, but the important thing is this. First, and it's not just for this class, it's for everything. Understand what you are doing. Don't remember all these details. Okay, yes, they are important, but you don't need to remember every detail. It's important here, okay, so what we are doing and why we are doing it. So I'm just gonna put it this thing again. Now just writing the Kalman gain. And then the thing gets like very compact to the point that actually this equation is known, right? So this was the fourth equation. I'm not gonna go up, but this should be something like this, right? This is the fourth equation. What is the mean of the posterior after considering the action and the observation, right? So this is a way of obtaining it. And then there's a final part, which is the covariance, right? And if you remember, the covariance that we are looking for is the Schur complement, right? After considering cross terms and other parts. So let me write it this way. I'm just substituting things from the joint Gaussian. This is, if I remember correctly, one of the cross terms. This is covariance of set inverse. And then what we have on this last term is the cross term of set X, maybe? Bless you. Okay. Doesn't want to work. I don't know. Okay, so this is the result. And now let's rearrange some of these things, right? In this case, what we can do is we can just substitute here the Kalman gain as we have defined it, right? So this is KT. And then if we do that, and then we take like this thing like it's in common on both places, we get this covariance, which is still being contracted, which is important. And this depends on the Kalman gain, right? Okay, so this, as defined on the equations, and I hope that now you are convinced, is what you get after doing the conditioning, right? So this is the fifth equation, right? Out of nowhere, the reason for doing this is just that, joint distribution that we are conditioning, right? So we are doing the full Bayesian derivation, and at the end we get exactly the same things. There's other derivations out there for the Kalman filter which are actually like looking for maximums, and then you do derivatives, and then you just equal them to 0, which is the kind of the standard thing, but you get exactly to the same result. And it's because the system is linear, right? So this is interesting. I think with this, you will never forget, after last lecture and today's lecture, right, how to derive the Kalman filter. If someone asks you, yeah, it's very simple. You just use the base filter and then apply joint Gaussian distributions, first for marginalizing and second for conditioning. Easy, right? But how to derive this? So we need to do like writing some parts here and there, and but now we are finished. So we know it's explained, I guess, I hope, clear for everyone, or at least there's like a lot of material. You can always review it later. You can always check with us, right? TAs or office hours, whatever you want. But please, it's what we do, right? It's not really forgetting one subindex, one inverted, but it's what we do, right? I think that's the interesting part. Yeah.
Are we going to extend the
Not today. But today, I think today, yeah, we're almost finished. But the extended Kalman filter, it's going to be just a consequence of what do we do with this nice algorithm, which is the best you can do with linear system, what you can do when you have a nonlinear system, right? So this is the first step, just as a hint or a spoiler, yeah, we are going to linearize and see what happens. So there's a lot of topics, a lot of papers that have been published like long time ago on this, but yeah, this is always an issue, right? So when you start linearizing and when you do assumptions, then this is not the optimal thing to do. Kalman filter will not be optimal for nonlinear. Actually, it's not the best thing you can do. There are other better things, which we will discuss. Okay, so just to recap a little, right? So Kalman filter is highly efficient. Remember that here we are marginalizing, we are conditioning, and it just turns out to be like some linear algebra operations, so we just need to do some inversions and multiplications, but actually for other distributions, you should be doing like sampling or other numerical methods to calculate the marginalization, and the same for the conditioning. So this is kind of amazing. Right? In fact, what we are doing here is we are inverting this. I mean, the complexity depends on the inversion of this matrix, right? And this actually depends on the number of observations. So if you remember, K was the number of, I mean, the dimensionality of the observation. And then, well, we have like some multiplications that depends on the state variable, right? But depends. Still, this is very efficient. This is optimal for linear systems. Okay, doesn't want to write. So this derivation, it's exactly the same as if you were doing optimization. I already said that. Unfortunately, the world is nonlinear, right? Even our systems that we are going to be using, these very first systems for motion transition functions on I don't know, like a planar things, or the observation functions that we are going to be using are nonlinear. So this is going to be a little trouble, but we'll see what we can do, right? And it's fairly used, right? Because it usually works if you take the proper considerations. And I think the most important one is considering the error correctly, right? So if you are like very far away, your linearization is going to be poor, so this is not the technique for you. We are going to describe like other kind of methods that are not based on linearization. But if some conditions are met, then you know that this is the most efficient thing you can do, right? Okay, what else? There was like another example here on the notes if you want to follow on the temperature of the system, right? So I'm just putting numbers to this thing that we are saying. So it's a one-dimensional Kalman filter. And I think the interesting thing is if you go to these numbers, you don't have to do it, right? This is just calculating things. What you will see is actually what happens with the distribution, right? So you initially have a prior which is very flat, right? You don't have like certainty on what's going on. But after doing like a propagation of the system, it's even flatter. It's kind of, well, some sort of diffusion process, if you want to think about it this way. You're basically losing certainty after you propagate. But when you add an observation, this certainty, I mean, the distributions become like thinner. That means that the covariances are bigger, right? And no, smaller. And that means that you have more information, right? So it's a kind of interesting process. You plot the prior, then you propagate it, just executing a command, and then you observe. And then you see how the distributions change, right? So one is shifted slightly to one side because the observation is telling you to do that, and then the covariance also change, right? So please follow this example. You will see like this with some, like, this is a very toy example, but at least you will get an idea of what's going on. Later, on problem set 2, you will be applying this, right? But it's important that you have the intuition of what's the filtering doing, like very strong and very well assimilated. Okay, so for next lecture. Tomorrow you can take a look at probabilistic robotics, chapters 5 and 6. We are going to explain like motion models, so what are these transition functions, and observation models. Okay, so see you tomorrow.